So when we talk about chapter 3, we're talking about chemical equations and chemical reactions. When we talk about chemical equations and chemical reactions, we want to give you first the format for them. Most of you already know this. And then the concepts of balancing, and then the types of reactions and so forth. So the concept of reactions involves a simple notation: reactants go to products. Sometimes these are written in empirical formats. A plus B goes to AB, indicating a combination or various such symbology. So this is the standard operating symbology that you're most likely familiar with. Now, within this, we have what we call the law of conservation of matter. And brief, matter is neither created nor destroyed. It only changes in form. When this is applied to chemical equations, we identify it as the law of mass balance. In essence, the sum of the masses of the reactants equal sum mass products. In other words, balance the equation. So, when balancing chemical equations, most of you are very familiar with the idea. The number of elements on the reactant side must match the number of elements on the product side. And I'm going to be very brief about this in its context, and we'll work a couple of problems, but for the most part, you practice as you need it. And there are two kinds of balancing. One, balance by inspection, and one where you balance by rules. And this essentially is oxidation and reduction, or redox reactions. And we will get to those hopefully today, show you the rules that are associated with that. Now, when we consider a chemical reaction, again, the sum of the masses of the reactants and products. So if we start out with something like a mixture of hydrogen gas and nitrogen gas, like this, and we make ammonia gas, okay? What do we have to do to balance this equation? Well, we look on the left side and the right side, and we see that the numbers of elements are different in the structure of the format. And so we need to increase or decrease the numbers of elements. Now, the subscripts, please be advised, do not change when you're given a formula, either in the polyions or in the molecular compounds, because the number identified with the subscript defines that substance. Okay, if you can't just simply come up here and put a 6 there and a 2 as a subscript. So the subscripts are assumed to be fixed in nature. So that leaves us with, well, how do I increase and decrease? We use coefficients. So if we have one nitrogen on the right side of the arrow, yields, I'm assuming that's, you know that, yields, and 2 on the left, we need to increase, and the only way to do that is put a 2 right there, and that increases not only the nitrogen, but it also increases everything behind that 2, as you well know, and so we're also talking about 6 hydrogens now. So over here we have 2 hydrogens, and so we need to increase that to 3. So that's the fundamental idea of how these concepts work. Now, most of you know the idea of atomic weights, and to get molecular weight, you add up atomic weights. So we want to check the sum of the atomic weights on the reactant side must equal the sum of the atomic weights on the product side, just to illustrate the issue. So we have 6 hydrogens plus 2 nitrogens, and the element symbols represent mass, is equal to 2 NH3 molecules and that contact. So we have 6 times 1 plus 2 times 14 must equal 2 times 14 plus 3 times 1, like that, and so that's 2834. And then we refer to that in atomic mass units, as we talked about when we talked about the periodic table and isotopes, stuff like that. So 50, 60, 17, that's 34 also. So here we find the sum of the mass of the reactants equal sum of the mass of the products. And so that's the fundamental idea as you go through these ideas and talk about it. And you don't really change the numbers of elements, but you change the form. Here we're talking about hydrogen gas, nitrogen gas, clear vapor, and ammonia. And most of you know what ammonia smells like from house cleaning ammonia. Quite the difference. Now, the next thing I want to emphasize, you may not know, in that why do we have to put hydrogen into this equation, in this format, H2, and why do we have to put nitrogen in as an N2? Anybody know that? Or why do we know that that's ammonia? That's only one form of ammonia is an NH3 there. So we, write it down in that context. Well, the reason is this is called the standard equation. And what's the standard equation? It is the equation of a reaction whereby the coefficients have been reduced to the smallest whole number ratio. Now, I can multiply through that by 2, and I still have the same reaction. It's just more stuff, but it's not a standard equation. Or I can divide everything by 2. But in presenting equations in standard form, and this is called a molecular equation in standard form, we reduce the coefficients to the smallest whole number ratio of substances in that reaction. Well, that's one aspect of this equation as a standard equation. The second of a standard equation is the form of the substances. The form of substances is what we call basic standard states. So we give you this rule right here. Molecular equations must be, of course, balanced. That's obviously rule 1 we just looked at. And in basic standard, STD, standard state. When we speak of something in basic standard state, it is the most common form of that substance, okay? So, by definition, now, basic standard states have what they call standard state enthalpies, or standard heats of formation. And it has a symbol, delta HF, with a little circle at the top of it, like that. Is the symbology of it. Very important definition that you understand. I'll show you what it means. And there are two rules that occur. One, if an element's, all elements, let me put it this way, all elements in basic standard state have a value of delta HF equal to 0 kilojoules per mole. Now, that may not mean anything at this moment, but it will in a minute. Compounds not and elements not in basic standard state have values not equal to 0. Not equal to 0. Basic standard state of elements and compounds are published in what we call the thermodynamics quantities table, or that up here for you. This is found, you can go online and Google thermodynamic quantities for substances or standard state, ether formation values. Google that, you'll get a gazillion citations. But they all are just like this one. And this one's in the back of your textbook. And it says, in the appendix, it says thermodynamic quantities for substances and ions at 25 degrees Celsius. Well, there are two standards in chemistry that we teach and try to get students to learn. One is what we call the gas law, STP, 0 degrees and 1 atmosphere. But there's also a thermodynamic standard. And thermodynamic temperature standard is 25 degrees Celsius. And so all these tables that you see back here are at 25 degrees. You can go over here and look at some others at other tables, and they have it the heading 25 degrees. That just means the data is based on a 25 degree thermodynamic standard. Okay, now as you look at this table, a couple of things should jump out at you. One, elements in basic standard state are 0. Well, I can find a 0, and the delta HF. This a little bit. Okay, see right here, you see the delta HF right there on the left, and kilojoules per mole, and disregard the electron thing. And if you come down here, you see a couple of zeros right here, okay? And then come over here to the left, and you see the element formula. Well, that's the basic standard state. Now, it may have several forms. Here's an ion of aluminum. Well, that has a number over here. It can be plus or minus. But only that substance right there that's 0 is the basic standard state of aluminum. Down here, you see barium, and it's the basic standard state of barium. So if you had aluminum in an equation, you want to write it in form of Al solid, S for solid. And same way with barium. If it's in a reaction, you find that formula and you use that in the molecular equation. And you can go on, and there's some others. You can see beryllium and boron, and we go on to many others in here that are listed. And you see here for one of them is bromine. Okay, now bromine has many forms. You see what we're talking about here, I'm sure. And the form of bromine that goes into a standard molecular equation is the basic standard state form. And so you look down here and you see 0, and it has to go into all of the molecular equations in the form of Br2, subscript 2. And so you're kind of bound to that based on the fact that it is a basic standard state, even though there are other forms of bromine, bromides, that are not in basic standard state, and those have numbers you see out to the side of them. Now, a moment ago I asked you, says, why do we have to put hydrogen in as H2 and nitrogen in as H2? Well, if we look at hydrogen and nitrogen, also in this collection, we'll find that hydrogen and nitrogen also have a 0 delta HF in their formulas. Let's see if I can find it. There's hydrogen right here. So you see here, hydrogen would have a 0 and nitrogen also. Okay. Yeah, here we go. And you can see nitrogen right here has a N2 form. Well, there's a unique way to find these on the periodic table if you don't know. Does anybody know how many diatomic basic standard state elements there are? There are 7. What does that symbol look like? 7. You just have to remember hydrogen's over here. It goes with it. Okay, so that's a very simple little memory device for remembering that hydrogen, nitrogen, oxygen, and the halogens have to go in as diatomic when writing a molecular equation. It must include those in diatomic form. And their delta HF values for all of the diatomics, standard heats of formation for, say, H2 gas is equal to 0 kilojoules per mole. And so everything else works from that. If it's an element not in basic standard state, it will have a number. For manganese in gas form has a value over here, 283 kilojoules. It's kind of like heating it up, pushing it into gas phase. We'll learn about that when we get to stoichiometry of reactions. And anyway, here is your standard form, and here it is in ionic form, and here's manganese oxide, where it is a compound. So compounds, there's only one of them. Now, the only difference is sometimes you have gas phase compound like water and steam. It'll have a different number than H2O in liquid form. So those energy numbers are very important to you later on. But the first step is to learn what we mean by basic standard state. You have basic standard states for elements, basic standard states for compounds, and then elements not in basic standard states that have numerical values of delta HF on them. So we'll learn more about how to use those in a different chapter. Okay, the point being is if I have an equation, say methane, in gas form, and oxygen in gas form, going to CO2 in gas form, and water in liquid form. I have to write oxygen as an O2 in that equation. Well, there is only one form of CH4, methane. There's one form of CO2 and one form of, well, actually there are two states, three states really, solid, liquid, gas. But I chose to put liquid form in there, and it'll have their own personal delta H number. Okay, so that's how you construct a molecular equation. And of course, in balancing this, carbons, 4 hydrogens. We need 4 hydrogens, so we'll put a 2 on that. And so now we have 4 oxygens, so I'll put a 2 right there. And so the standard state equation is balanced in that context. And there's one other factoid that I need to share. It is assumed that the standard state equation is at 0 degrees Celsius and 1 atmosphere pressure. When a molecular equation is given to you, balanced in a problem or so, you would just, and nothing else, I mean, of course, other data may be given, but it doesn't specify that it is at 0 degrees and 1 atmosphere. It may say at STP, but that's 0 degrees and 1 atmosphere, but it may not. But as you're given an equation in standard state, you mentally assume that it is at 0 degrees and 1 atmosphere. Now the reason is primarily for gas phase components in here. The oxygen exists as well, methane and CO2 all exist in gas. There is a numerical value for what we call a molar volume, and that only occurs at 0 degrees and 1 atmosphere. A molar volume, symbolized by capital V subscript M, is defined as the volume occupied by 1 molar mass of gas phase substance. Now, I visualize this in my head as something like a basketball. It's a spherical object. And the basketball is recognized and pretty familiar with that size. Well, that's about 1 molar volume at 0 degrees in 1 atmosphere. And that has a value, some of you may know, 22.4 liters. So 1 VM at 0 degrees Celsius and 1 atmosphere is equal to 22.4 liters. Now, if you're not at 0 degrees in 1 atmosphere, the gas is not going to occupy 22.4. If you're warmer than that, gas expands. So you have a bigger number. If you're colder than 0 degrees, minus 10, you have a smaller volume. And so that, in essence, is the reason we have specify this at 0 degrees, so there's a place to start in the quantitative analysis of an equation. One is to assume this is at 0 degrees and 1 atmosphere, so that if you have gas phase, you know that if it's a 1 right there, that's 1 molar volume. A 2 represents 2 molar volumes. 1 molar volume, and then that's 2, well, it's 2 liquids. Well, liquids doesn't count because liquids and solids are not molar volumes. They only apply to gases. So we can say this is 22.4 liters at STP. That's what STP is, 0 and 1. And this is 44.8, 2 times 22.4 liters. And CO2, again, is 22.4. Now, beyond that, we will take up more later on when we get to gas laws. But that is, when we're talking about chemical equations, one of the things you do need to know. The reason it's given a standard state evaluation is so that you will assume it to be at 0 degrees and 1 atmosphere. If it's anything else than that, it'll tell you. Okay? But as it's written, it's given in 0 degrees and 1 atmosphere. That's the end of the story on that.